shorter. Shorter. I noticed. Okay, ladies and jelly beans, let's make a start. Good afternoon, everybody. Yes, hello. And this week I would like to get started with a bit of a new topic. Many of you will have done that at A-level or even GCSE. It's just a little bit of a revision. So, I thought I could hear myself talking. You see? And at 100%, wow. Good, so let's get started again. So in this first session, I would like to do a quick revision of acids and bases. We are going to look at strong acids and strong bases. We will do a little bit of pH calculations. You have done that, yes? Fine, we can go very quickly through that. And in the second session, I want to discuss with you what happens if we are not dealing with a strong acid or base. And then we obviously have to take a slightly different approach. So let's just simply quick through that stuff, whiz through it fairly swiftly. So acid and bases, you are all familiar with the definition of what is an acid, what is a base. The original definition by Arrhenius was that an acid turns an indicator in water red, and a base turns it blue. But at that point, people didn't really understand what is an acid, and that only changed with the definition of Bronsted. Where they have this weird O with a line through it. And Bronsted said An acid is everything that is a proton donor. So acid is a proton donor. And the base is everything that accepts protons. So it's a proton acceptor. And this then has been a little bit refined later on by Lewis. Lewis said an acid is an electron pair acceptor. A base is an electron pair donor. But that's not so much of relevance in a biological context. The Brønsted definition is probably the one that you really need to understand what this is all about. And we are usually dealing with bases and acids in water, in biological systems. Although sometimes the solution might be more alcohol. This is usually on a Wednesday night. When students go to Wednesday at the venue, then there is probably not so much water in the blood, it's more alcohol in the blood. But still the same rules apply to acids and bases. When is a substance an acid? When does it voluntarily give up its protons? This, of course, depends very much on the electronegativity of the substance. So let's have, for example, HCl. And I indicate that like this. And in this case, the chloride ion has a very high electronegativity. So it really wants electrons. Whereas the hydrogen doesn't have such a high electronegativity. It basically says, yeah, if you really must have my electron, just take it. So it's probably you could liken it to almost a sort of an abusive relationship between the hydrogen and the chloride. The chloride says, give me your electrons. Right? This one. And then out. So hydrochloric acid would dissociate into chloride plus the proton. And I think when we are dealing with solutions or acids in water, we should be aware that naked protons don't exist. Naked ions don't exist. They are all surrounded by a huge huge gathering of water around them. So what this exactly would look like, we don't really know because it changes very quickly. So it's quite difficult to analyze what does, for example, a proton in a water environment look like. Some people denote it as, for example, HCl plus water. They denote that as chloride plus H3O plus. But this is just, it could be H71O35 or something like that. It just indicates that there is lots of water around, a water cloud around the proton. And of course, the chloride is also surrounded by water, so very often people indicate that by just simply writing AQ, which stands for watery environment in this case. Okay, so if we are looking at this reaction, HCl plus water, hydrochloric acid in water, we find that in the case of a very strong acid, all of the acid, or almost all of the acid, will dissociate. So if I start off, let's say, with 100 molecules of HCl plus water, and strictly speaking, it can go either way. It can go backwards and forwards, so that's why I denote it with this double arrow. We start with 100 molecules of HCl. What we will find once we have reached an equilibrium is that we have maybe, so that's the start, at the end of the reaction, when the reaction has reached a sort of a plateau, when nothing further happens, when we have reached an equilibrium, at equilibrium we find that we probably have one HCl left and we have, how many chlorides do we have? 99 exactly. So we have 99 chlorides because it must give us the 100. How many of the protons do we have? 99. It's like Nena says, 99 red balloons. If at all. In the case of hydrochloric acid, it's probably, you can't do that with 101. I just wanted to illustrate that here. In the case of hydrochloride, it is probably 99.999999% have dissociated. And what's quite important is that when we have this reaction, HCl plus water, Cl minus plus H3O plus, in the case of a very strong acid, we can assume that basically everything of the acid is dissociated. So strong acid means that every single acid molecule is dissociated. Dissociated. And we also have the case with hydrochloric acid that one molecule HCl gives us one molecule Cl minus and one molecule protons. We call this a monoprotic acid. Why monoprotic? Just simply because it delivers one proton. Of course, we can have diprotic acids. So, for example, H2SO4. So if I start with a concentration of 1 mole per liter of H2SO4, what would be my concentration of SO4 2 minus? What would be my concentration of the sulfate? in the negatively charged form. Simple. It's also 1 mole per liter. But what about the protons? How many have I got? 2. So I have 2 protons, and now my proton concentration would be 2 mole per liter. Because each one molecule of sulfuric acid produces 2 protons. Make sense? Pretty straightforward. Okay. Now, we can very easily measure proton concentrations, and you will do that in one of the practicals. I think it is in practical in week 7, where you have a little pH electrode, and that allows you to measure the proton concentration. And it's quite accurate. But very often you will find that you are dealing with extremely small numbers. And dealing with small numbers, chemists don't like that. So what they have introduced is the concept of pH. And you have heard about that. The definition of pH is the negative log to the basis of 10 of the proton concentration. So that is the definition of pH. And that is where a lot of people have sort of, where they don't feel too well, so that they start coughing. The proton concentration always has to be in mole per liter or molar. It always has to be in molar. If you have a proton concentration in millimole per liter, it's not going to work. You always have to convert it into mole per liter. Absolutely essential. So, let's say you have a proton concentration, and sometimes I just simply abbreviate that with the square brackets. Your proton concentration is 1 times 10 to the minus 2 molar. What is the pH of this? You have to do the calculation. Get your calculators out. Got it? Easy. So what did you get? 2. So let's put that in. pH equals minus log of 1 times 10 to the minus 2. We don't write the m because your calculator just simply can't deal with log and text. So pH is always without a unit, because the assumption is that it has been derived from mole per liter. So minus log 10 to the minus 2, that gives you minus, and log 1 times 10 to the minus 2 gives you negative 2. Minus times minus gives you therefore pH of 2. Okay? Very easy. Gets a little bit more interesting if you have a proton concentration equals 0.5 molar. What's the pH? What is the pH? 0.3. Just simply negative log of 0.5. What's the pH of 0.5 millimolar? pH equals 3.3. Oh, did I say? Yeah, 3.3. You just put in, make sure that you do it the right way around, equals negative log of 0.5 times 10 to the minus 3. And this times to the minus 3, that's the milli, and that's absolutely essential. You must do that. You can't leave it as just simply 0.5, because otherwise you would get what we just done before. You have a pH equals 4. What is the concentration of the protons? So how do you convert log into not log? So here you have pH equals 4 equals minus log of the proton concentration. How do we get this proton concentration out of the log? The answer is, what is the inverse, what is the mathematically inverse operation to log? What's the inverse operation to log? 10 to the power, not minus in this case. Just I was asking for the log. So log inverse operation. If it is the log to the basis of 10, then the inverse operation is 10 to the power of, and I indicate that with a 10 and a little hat up. Yeah? So what I do here in order to get this out, first I bring the minus sign to the other side. I just simply multiply both sides of this equation by -1. Then I have -4 equals log proton concentration. And then I take both sides 10 to the power of. So I have 10 to the power of -4 equals 10 to the power of log proton. And basically, like with fractions, the inverse operation cancels out the operation. So 10 and log cancel each other out. And all I've got here then is the proton concentration. Or if you want to write it in a slightly different form, proton concentration equals 10 to the -4 what? Bananas? Turkeys? Moles? Molar. Molar. Mole per liter. Yeah? Don't just simply brush that under the carpet. That's really important, this thing. Okay? Happy with that? So you have a pH equals 3.5. What's the proton concentration? Thank you. 3.16 times 10 to -4. Thank you. So 3.5 equals minus log of proton. Bring the negative side to the other side. So we have minus 3.5 equals log proton. We take both sides 10 to the power of. We have 10 to the minus 3.5 equals 10 to the log of the proton concentration. 10 and log cancel out. And we have proton concentration equals 10 to the power of minus 3.5 molar, and that is the same as 3.16 times 10 to the minus 4 molar. Did I get the right number? Yeah. Is it right? Okay, so fantastic. We don't have to worry about that. You can easily convert pH and protons into each other. Now, what happens if we have not an acid, if we have a base? So, for example, we might have NH3 plus water and this gives us NH4 plus OH minus. Okay? Again, we have a very almost identical situation. We have a stoichiometric relationship. One molecule of this Ammonia gives us one molecule of the ammonia and the hydroxide ions. And in this case, the NH3 has accepted the proton from the water, so we know it's a base. We can very easily do the same thing that we just done with the pH. We can define, instead of pH, we can define a POH. And the POH is minus log of the hydroxide concentration. And again, this has to be in mole per liter or molar. Okay, happy with that? Very simple. So if you have a pH of, let's say, pH is 3.5, what's the corresponding POH? 10.5, thank you very much. So it's just simply, I haven't told you that. The correlation between pH and POH is that the sum of pH plus POH is always 14. Yeah? That is what I haven't mentioned, but you're absolutely right. So the two together are 14. It's not one of life's mysteries. There is a totally perfectly acceptable explanation for that. But for the time being, I just want you to remember pH plus POH equals 14. So you can very easily convert pH into POH and the other way around. Make sense? Yeah, you've done that GCSE. Is that GCSE stuff? A-level. Really? Oh. But you have done all A-level chemistry, don't you? Ah. So is that new for you guys? That is new. The whole thing is new. Ah, okay. Okay. Okay, for those of you to whom this is new, does it make sense so far? No. Okay, where do I start then? How do I tell it my children? Okay, let's go back to HCl. H plus plus Cl minus. Does that make sense so far? That it dissociates? Does that make sense? No? Yes. I'm looking at people who haven't done A-level. Does that make sense? That it dissociates? Yeah? Does this make sense? Does this make sense? Why I do the cancelling thing. Gotcha. Good. Excellent. Thank you. Let's do a simple example. X plus 5 equals 20. I'm pretty sure you can solve that, can't you? How do you actually solve an equation like that? What you do is you are trying to get rid of this guy here, this plus 5. Right? Because you want all the x's on one side and all the other crap on the other side. How do you do that? Well, what you do is you say, okay, I have a plus 5 on this side. So I do exactly the inverse mathematical operation because then they cancel each other out. So in this case, what I would do is the inverse mathematical operation to plus is what? It's minus. Minus 5. So I have x plus 5 minus 5 equals 20 minus 5. Yeah? That's the sort of the really long-winded way. Does it make sense? Yeah? So plus 5 and minus 5 eliminate each other. I like that sound. I think that sounds a little bit like Dr. Carden the other day. I spoke to him after the lectures, and God, he was in a poor state. So we have x equals 15. Okay, here's another one for you guys. 5x equals 20. What do I have to do in order to get rid of the 5? I divide it by 5. Why do you say that? Because I have 5 times, and the inverse operation of times is division. So, how do I write that? Divided by 5. So what I have is 5x divided by 5, and I just simply write it like that, equals 20 divided by 5. What happens to the 5 on the left-hand side? They cancel each other. By using the inverse operation, they eliminate each other. And all I have left is x equals 20 over 5, and that's 4. I can do that in my head. Yeah? Make sense? So I have 2 equals log x. What is the inverse operation to log? We just said it is 10 to the power of. So we have 10 to the power of 2 equals 10 to the power of log x. And as in the previous examples, 10 and log eliminate each other. So what we have is 10 to the power of 2 equals x. Make sense? Sort of? Yeah? I will email you a lot of practice questions where you can practice this stuff, how you can convert things. Okay? Ah, the connection is weak again. I was waiting for that. So, in water, when we have a solution, acid or base, in water, we have pH plus POH equals 14. And we can easily convert pH and POH into each other. We also, in water, have a nice scale from, let's say, 0 to 7 to 14. That is probably what you are familiar with. That is the pH scale. Yeah? And we say everything below 7 is acidic. Everything above 7 is basic. Okay? Makes sense? What is 7? Neutral. Neither here nor there. So 7 is neutral. Oh, just a quick question. For pH, can it be smaller than 0? Yes. Yes. How?
Because the concentration is a log function because it's minus. So if the concentration of hydrogen atoms is greater than 1 minus a log, the log will be positive, so it will be minus plus, which is minus.
I could not have said it any better. You probably didn't hear that, but you are absolutely right. If, for example, the proton concentration is larger than 1 molar, let's say we have a proton concentration, is it still working? We have a proton concentration of 10 molar. What is the pH? What is the pH? So all we need to do is minus log or negative log of 10. Log 10 is 1. So the pH in this case would be negative 1. Okay? Happy with that? Fantastic. Now let's look at something really weird, at a totally weird substance. This substance is actually the chemical compound that on this planet causes the most deaths. It is absolutely toxic in the wrong hands. It is dihydrogen monoxide. Dihydrogen monoxide. It's not alcohol. It's water. Many people are killed by water, right? Now, you can also sometimes see that people, you can try that with your housemates. Try that with your housemates, especially when they are a little bit sort of, my body is a temple. I won't let any dangerous chemicals get into my body. And then you can tell them, you know, there is this really dangerous compound that they just consumed, dihydrogen monoxide. It's absolutely deadly. And they freak out, and it's brilliant. Just watch them, you know. So, water. What can water do? Well, water can act as an acid. H plus or H3O plus OH minus. Yeah, so we have two waters. One of the waters, have I made a mistake? No. It is balanced. No, what I'm saying is that one water, this guy here, H1, let's just, there, HOH, HO2, this one is giving up its proton. Yeah? So what we have here is an OH minus on top and an H3O plus at the bottom. So one water gives up its proton. So this guy here, this HOH, what is it? Acid or base? The water that gives up a proton. What is it? It's an acid. So in this case, the water gives up the proton, and therefore it is an acid. So water is acidic. At the same time, this guy here, it picks up the proton so something that picks up a proton, what is that? It's a base. Hey, wait a moment. Wait, whoa. You just told me that it is an acid, and now you say it's a base. WTF, can you please make up your mind? What is it, base or acid? It's both. If a substance is both, it's called amphoteric. It can be an acid or both at the same time. So water is the typical amphoteric substance. So it can donate a proton, so it can be an acid, it can be a base. Can be acid or base. Okay? Now when we look at water, and I just write it like that, H plus plus OH minus, we find that in normal water, without any frills or anything like that, the concentration of protons is 1 times 10 to the minus 7 molar. Okay? Trick question. What is the concentration of the OH minus? Loud? It's the same. Why? Just for a simple reason, if you split this guy here, the water, if you split that, you got the same amount of protons and OH minus. Yeah? Can you just quickly, before the break, can you just quickly calculate what is the pH of water? Surprise! Surprise! Okay, let's quickly do that. Minus log of protons minus log of 10 to the minus 7. So the pH of water equals 7. What's the pOH? 7. Okay? And if you add them together, what does it give you? Ha! 14. A miracle has happened. Make sense? Okay, before I let you go into your break, I want you just simply quickly calculate pH of a 1 molar hydrochloric acid solution. Now we don't have just the protons given, we just have instead, we have the concentration of the acid. Yeah? Previously I've given you the proton concentration and asked for the pH. Now I give you the acid concentration. How are we going to deal with that? Well, actually, it's not a big problem because we know that 1 molar hydrochloric acid, what is the concentration of the protons in this case? 1 what? Bananas? Concentration of the protons is 1 molar, and the concentration of the chlorides is also 1 molar. So what's the pH of a 1 molar hydrochloric acid? 0. pH equals minus log of 1 equals 0. So pH of a 1 molar hydrochloric acid is 0. With that, we have a 10-minute break. You come back, and then I show you something that will blow your mind. And if it doesn't blow your mind, you have no emotion.